Hi everyone and welcome back to Physics 4A. Today we are going to talk about potential energy and conservation of energy. So let's go ahead and start with the idea of the potential energy of a system. Now I want to first draw your attention to this diagram. Okay, so we have this football player kicking a football up into the air until somebody catches it out there. Okay, and we want to note what is going on at each stage. So at this first stage, you have the kicker who does work on the ball, and it gives it a maximum kinetic energy, and the potential energy is minimum. Okay, as the ball goes along its path here, its projectile, the ball goes up, the kinetic energy decreases, and the potential energy increases. Okay, at the highest peak here, we have a maximum potential energy and a kinetic energy at its minimum. And then as the ball descends, the kinetic energy increases again. Because the ball is gaining speed, the potential energy is decreasing. And as the receiver catches the ball, the kinetic energy is at maximum and the potential energy is at minimum again. Okay, so remember that kinetic energy is equal to 1/2 mv squared. Okay, and that is where we are getting this idea that the kinetic energy is related to its velocity. Okay, and the kinetic energy at its maximum here, at this maximum point, is going to be at a minimum since our velocity will go to 0 here. Okay, and at the starting points, we have the highest velocities. So this is where we have a V max, V min. Okay, so this is how we are looking at kinetic energy. So we saw that last time. Potential energy is all about work being done. Okay, and we'll talk about more specific how to calculate them, the potential energies in a system, here in a moment. But just to get the idea that we have a potential energy difference, okay, and we define that as the final potential energy minus the initial potential energy, and it is equal to negative the work from the initial to the final. Okay. And again, the change in our potential energy, U, is equal to the the final potential energy minus the initial potential energy. And R here is just representing where it is in this path. Okay. Oops. Now, potential energy with no friction or air resistance should be related to kinetic energy in this way. The change in kinetic energy is equal to minus the change in potential energy. Okay, and we'll see in a moment that our total energy, I guess I should write it over here, total energy is equal to the change in kinetic energy plus the change in potential energy. Okay, I guess it would be change in energy. Okay, so we'll look at this a bit more in a little bit. Excuse me. All right, let's go ahead and do an example real quick to get the ball rolling. It states a particle moves along the x-axis under the action of a force given by this equation, where A equals 3 Newton per meter squared. Okay, what is the difference in its potential energy as it moves from this point to this point? Okay, so the difference in potential energy. Let me change pen color. This is a little bit too dark. Let's see. We'll do white. All right. So our change in potential energy from A to B, we just defined it as the negative work from A to B, okay? If you remember from last time, we were able to define work in terms of force, okay? So remember that our work was an integral from A to B of our force times dx, okay? Or displacement. Okay, so we can use this equation, this idea, to solve for our potential energy as it moves from point A to point B. Okay, so let's go ahead and do that. We have an integral from 1 meter to 2 meters of F, which is negative A, which is 3x squared dx, and the units on this term here is Newton per meter squared, and these are the units of meters and meters, so this should turn out fine. So we have a positive now, 3 times x cubed over 3 from 1 to 2. Okay, so 3's cross out. We get 2 cubed minus 1 cubed, or 8 minus 1, which should be 7. Okay, so our difference here is going to be actually a positive value in potential energy from point A to point B, and potential energy is also going to be in joules. Okay. Sorry about that. I'm not sure what happened. But we have our difference in potential energy, 7J, and we have now part B that states what is the particle's potential energy at x equals 1 meter with respect to a given 0.5 joules of potential energy at x equals 0. Okay, so what we'll need to do is we'll need to find a equation that describes this motion. Okay, so previously we found this integral here, okay, and if we didn't have any boundaries here, our integral would give us this, let's see, of x, it would be x cubed, right, because our 3's would cancel, plus some constant. Okay, now we know that at u of 0 it equals 0.5 joules. Okay, so we'll use this in order to solve this problem here. Okay, so we have u of 0 is equal to 0 to the third plus some constant, and that should equal 0.5 joules. Okay, so this makes the constant equal to 0.5 joules here. Okay, so now u, or I should put it down here, constant equals 0.5 joules. Now u of 1 meter is going to be 1 cubed plus our constant, which is 0.5 joules. Okay, and so that means our potential energy at this point is going to be 1.5 joules. Okay? All right. So let's go ahead and move on to different types of potential energy. So we need to first go back and remember that work done by gravitational force is equal to negative mg times the difference in height. Okay, so we can use that and now state that our difference in our gravitational potential energy is minus the work done by gravitational force from A to B is equal to mg times the difference in height. Okay, now near Earth's surface, sorry about that. Near Earth's surface, we have that y sub a would be 0. Okay, and so we have mg times y plus a constant. Okay. All right. So using that, we can go ahead and solve for this next example, 8.2. It states that a 75 kilogram hiker ascends from the base of the summit, which would be here. Oops, that's in white, but you can see where I put the X. What is the gravitational potential energy of the hiker Earth system with respect to zero gravitational potential energy at the base of the height when the hiker is at the base of the hill, at the summit, and at sea level afterward? Okay, so our potential energy here, U, remember, is going to be this equation here, mgy. Okay, now at the base of the hill, it states that we are looking at this as the zero gravitational potential energy is going to be at the base height. So we can go ahead and say mu at base, I'll say, is 0 joules. Okay, so that takes care of the first one, right? So U at, we're going to call the base 0 meters, is equal to 0 joules, which makes sense if we plug mg times 0 meters in. That'll give us 0 joules. Okay, now the next part says at the summit. So the summit is 147 meters up. So our U is equal to mgy, which is 75 kilograms times 9.8 meters per second squared, times our height, 147. Okay, and that gives us, let me put that into my calculator really quick. 75 times 9.8 times 147. We get 108,000 joules, or we can say 108 kilojoules. Okay, now at sea level, we have, let's see, same idea here. Our y, though, is going to be negative since we are lower than the base. This states here that the summit is 195 meters above sea level. Okay, so when we find our y, it is actually going to be the difference between our base and our sea level and our summit. Okay, so let's see. Or this distance minus this distance. That'll give us our sea level. So 147 meters minus 195 meters. Okay. All right, so this gives us minus 35.3 kilojoules.